you by thesis123.com. I learn and teach online.
Here's the next question, number 52. In the signal flow diagram given in the figure, U1 and U2 are possible inputs, whereas Y1 and Y2 are possible outputs. When would the SISO system, or SISO, that single input, single output system, derived from this diagram be controllable and observable? Two aspects here, controllable and observable. We will have to take into consideration the entire system and see for what inputs and for what outputs would the system be controllable and observable. Okay, so we have our options given to us. A, when U1 is the only input and Y1 is the only output. B, when U2 is the only input and Y1 is the only output. C, when U1 is the only input and Y2 is the only output. And D, when U2 is the only input and Y2 is the only output. 4 different combinations. So we will have to check for each one of these options. Okay, so let's begin by first writing down the matrix equation from the block diagram given to us. I'll note it down here. Alright, so in general, our equation should be in the form x dot is equal to ax plus bu. So first we will write down from the given block diagram this expression here for both inputs as well as the output equation. So first let's start with the input equation. So we have x1 dot x2 dot is equal to, this is going to be our matrix A. X is x1 x2 plus, we have a matrix here for U1 and a matrix here for U2. Now let's find out what values go into these matrices, looking at the diagram here. Okay, so first observe the nodes at x1 and x2. So we have the values 5, observe 5, minus 2, 2 and 1. That's for x1 and x2. I'll just circle it so that you would know what I'm talking about. Okay, so here we have the value 5 from x1 and then we have the value minus 2 here. That's between these two nodes, and then we have the value 2 here between x1 and this node, and then the value here 1 x2. Now arranging them in order for x1 x2, we would have them as 5 minus 2, see that's correspondingly to x1 x2, and then 2 1 again corresponding to x1 and x2. If you will see there, observe the block diagram and your matrix. So this is our matrix A. Next we need for U1. Now observe where U1 is. U1, you have two values there, two paths. Both paths have a value of 1 each, right? Okay, so that means we have our matrix 1 1. Next, U2. U2 has got only one path and the value of that is 1. I think I missed writing that here. The value of that is 1. It doesn't have a connection to U1. Therefore, here the matrix is 0, 1. Okay, so this is our input equation. Let's write down our output. Output equation is written as y is equal to cx here. So write it down in matrix form. So that's y1 y2 is equal to a matrix C and then we have x1, x2. Let's look at our a block diagram again. Okay, so here we have y1, the value 1 from x1, if you'll observe. That's the only thing that is available from x1 in terms of y1 here. x1, y1, we have a value 1. Now to y2, we have two values. We have one path coming from x1, and then we have another coming from x2 at -1. So if we enter those values here, we would now have 1, 0, 1, -1. Okay, 1, 0, 1, -1. So I hope that is clear. So we have our output equation here, y is equal to cx plus some d. So here let's just put that as 0. That's alright. So this is our most important part, cx. Okay, so we'll start by figuring out what controllability is before we go into the check of controllability. Controllability of a system. Okay, so a system is said to be controllable if at a certain time t, let's take that as t naught, I'll write that down, at a certain time t naught, if it is possible for the system to transfer the system from a certain initial state. So we can take that state as x naught, from any initial state x naught to any other state, in a finite period of time, finite interval of time. Such a system is said to be controllable. If you can transfer the system from x naught to another state x in that certain in a particular interval of time, then it is said to be controllable. Now controllability of the system depends on this matrix A. It depends on A. And the control influence is the matrix B. So in order to check for the controllability, both matrices A and B are important. Okay, so now we'll start with the check on controllability. We start with a matrix QC. So this QC is the check for controllability. Now QC is written as a matrix of B, AB, A square B, A cube B, and so on. It goes on and on. Okay, so QC matrix is built in this way. It starts with the matrix B, then the multiplication of AB, then A square B, A cube B, and so on and so forth. But where do we stop? We stop with the order of QC. Now the order of QC is equal to the order of A. Order of QC is equal to the order of matrix A. Now our matrix A is a 2 by 2 matrix, therefore the order of A is 2, which means that the order of QC is also 2. So we stop with just two parts, which means that QC is built with B, matrix B, and then A, B. This is going to be our matrix of QC. So first, let's build this. Now, how do we say that this proves that it is that the system is controllable? Now, if once we build our matrix for QC, and if we see that the rank of QC is equal to the same order 2 of A, order of A, then the system is said to be controllable. So let's work on that. We have to show that det of Qc is non-zero. So this is what proves that the system is controllable. Okay, so here let's start with forming the matrix Qc. So we have two cases here. Now the options, as we have seen, we are working on the controllability, right? So we will be working on the inputs here. The input is, we have 4 different cases of A, B, C, D, U1, U2, U1 and U2, right? Those are the inputs. So let's start with when U1 is the input. We have to check for both. So we'll start first with U1 is the input. When U1 is the input, we already have our matrix B from what we have written earlier. Matrix B is 1, 1 or 0, 1 corresponding to U1 or U2. So since we are starting with the input of U1, the matrix would be here, this one, 1, 1. So that is our matrix B. Okay. So here we have B is equal to 1, 1. Now we have to figure out what is AB. So that's the multiplication of A, which is 5 minus 2, 2, 1, and then B, 1, 1. Now we multiply and we will get the matrix as 3, 3. Okay. Next, let's plug both these into the QC matrix. QC is now, first we have B, then we have AB, 3, 3. Okay, so this is right. So we have B and we have AB. So this is our QC matrix of 1, 1, 3, 3. Okay, so next let's find out the determinant of Qc. Now determinant of Qc would be, we know that, right? So that's AD minus BC, which is 3 minus 3, and that gives us 0. Now it is not supposed to be equal to 0, which means that U1 is not the right input. So this checks out wrong. Next step, when U2 is the input. Okay, so let's do that next. Right, so when U2 is the input. So when U2 is the input, we have the matrix B as, let's see, what do we have there? Corresponding to U2, we have the matrix as 0, 1. Do you see that? This one here, okay? So that's 0, 1. And then we have AB. Okay, so let's multiply. So we have A, 5 minus 2, 2, 1, multiplied by 0 and 1. And that gives us minus 2 and 1. Okay? Right. Next, let's write down the matrix for QC. So QC is the same as earlier. We have B and then AB. It is built this way. And then B, we enter 0, 1, and then minus 2 and 1. Okay, so we have our 2 by 2 matrix of QC. Next step, find the determinant of QC. So the determinant of QC now is 2, which is a non-zero, and it is equal to the rank of A, the order of A, which means this checks out to be right. So the system is controllable. The system is controllable when the input is U2. So it is not U1, it is U2. 2. Now the next thing is to work on the observability. Now let's see when the system is observable. So before that, we'll talk about what observability is. So a system is said to be observable at a certain time t0 if the system is at a certain state, say x of t0. So I think I'll write it down and then we'll talk about it. So a system is said to be observable at time t0 if with the system in a certain state, let's say x of t0, it is possible to determine this state from observations of the output over a finite interval of time. Okay, so such a system is said to be observable. Now what this actually means is, now let's say that we have from our system we have noted down certain measurements, a finite set of measurements from the system. So if we are able to reconstruct it to obtain the initial condition of the system, then such a system is said to be observable. Okay, so using the output observations and trying to get the system in a certain state, that is x of t1, then it is called observable, that the system is said to be observable. Now, in order to check if the system is observable, it depends upon the system matrix A and the output matrix C. Here. So it depends on the matrix A and the output matrix C. So now let's start with the check. Okay. So in the previous part, when we were working on controllability, we found a matrix Qc. In this case, we are going to work out a matrix Q0. So Q0 is equal to, we build it based on the output matrix C, but transpose of it. So C transpose, and then we have A transpose, C transpose, and then we have A transpose square, C transpose, A transpose cube, C transpose, and so on. So this actually goes on, but where do we stop? We stop when we reach the order of matrix A. Okay, so we stop when the order of this matrix equals the order of Q0 equals order of matrix A. Quite similar to the previous part. Okay, so in this case, Q0 equals C transpose, A transpose, C transpose, because the order of matrix A is 2. Okay, so in order to check if this system that we have here is observable, the rank of Q0 must be equal to the order of matrix A. So in other words, det of Q0 should not be equal to 0. It should be a non-zero value. Okay, so let's work it out. We start by finding out for two different outputs. So we have y1 and we have y2, right? So let's take y1 first. For output y1. Okay, so for output y1, what we have? We have first CT. Let's find out the transpose of CT here. Okay, so C is the matrix there, 1, 0, 1, minus 1. So the transpose of that, you know what transpose of a matrix is, right? Transpose is the interchanging of rows and columns, the elements of rows and columns. So here we have 1, 1, 0, minus 1. This is the transpose of C. Then we need the transpose of A. A transpose, what's A here? A is 5, minus 2, 2 and 1. And that becomes 5, 2, minus 2, 1. This is our transpose. So when we are calculating for the output of y1, we will have to take into consideration, okay, I want you to see this very carefully, one moment, just get to that point. Right, okay, so please look at this output equation here. y1, y2 equals 1, 0, 1, minus 1 for x1 and x2. So we have to take it corresponding to x1 and x2, which means now for output y1, we are going to take just this portion here, the first column, okay? So here for y1, CT is 1, 0. Next we calculate what is A transpose, C transpose. Let's multiply 5, 2, minus 2, 1 into 1, 0. This should give us 5 and minus 2. Okay, so C transpose and A transpose, C transpose, we have our two matrices here. Okay, so the next step is to formulate our Q naught. So Q naught is C transpose, it's a 2 by 2 matrix, so we can just substitute. Let's see now, Q naught is C transpose and A transpose, C transpose, right? So Q naught is now, let's see now, what is C transpose? We have 1, 0 there, so that's 1, 0. A transpose, C transpose is 5 minus 2. So the next step, calculate det of Q naught. So the determinant of Q naught is, when you calculate it, you will get minus 2. Now minus 2 is not equal to 0. It's a non-zero value. So which means that the system is observable when Q naught equals minus 2. And system is observable for the output value of y1. So we already have it. We don't have to calculate for y2. y2 would be equal to 0. So in this case, system is observable for y1 being the output. So what are the conditions that we found out? We found for the system to be both controllable and observable, our input should be y2, u2 is the input and y1 is the output. These are the right conditions. Okay, so let's see which is the right option in our options here. Okay, so we have here, let's see, u2 and y1. So when u2 is the only input and y1 is the only output, so option B is the right answer. Well, this is the entire solution and I really hope it has helped.
Thank you for watching this video. For future videos, please click here to subscribe YouTube channel. Visit our site thesis123.com for free student project or research ideas and online training. Follow us Facebook, Twitter, Google+ and Pinterest.